Okay, so we're going to try this again. The last video did not have sound. As I walk through this video, I suggest just kind of walking through the notes with me. You can just kind of fill it out as we go. If you need to pause because you need more time to write something, that's fine. And then hopefully we'll get through this quickly. So when we're talking about gases, this kind of goes along with gases because we're really going to focus now on what's actually, how do we get a gas? What kind of phase changes take place for a gas? So the first thing is just making sure we understand what our phase changes. So remember, phase changes are physical change. Physical change, okay, meaning that we are only changing the state of matter. We're not actually changing the substance. So not changing the substance. If you need to write that down to help you remember, that's fine. So like, for example, if this was water, if we're looking at water in this picture, right, this would be like solid ice. This would be a liquid water, like, water bottle. And then we have actual water vapor. Okay, like when it's very humid outside, that means there's a lot of gaseous water vapor in the air. You're probably familiar with a lot of these terms like melting, freezing, condensation, vaporization. Condensation is going from a gas to a liquid. So if you have a really cold, glass of water or drink or something, you're outside when it's hot, you'll notice that glass or cup, it kind of starts to sweat, right? It kind of gets that water on the outside of the cup. Well, what's actually happening, it doesn't have anything to do with what's inside the cup. It's actually the water vapor in the air, the liquid, or the gaseous water in the air turns into a liquid because as it comes in contact with that cold cup, it starts to cool down. Okay, so one thing to make sure we understand is that as we kind of move this way, we're adding energy or heat to our system. Okay, remember our kinetic energy, as our temperature increases, our kinetic energy is increasing. So we're kind of adding energy as we move to the right. As we move to the left, right, we're taking away energy, which makes sense. If I have gas particles that are moving around really fast, if I take some of their energy away, they're going to start to slow down until they turn into a liquid, then eventually into a solid. Okay, vaporization, there's two ways that you're probably familiar with this: boiling and also evaporation. Okay, one thing that's different is boiling, you're actually heating up the entire cup or pot or bowl, all of the water, the entire volume. And so that's why you get those rolling bubbles. Those are actually those particles, right, that are trying to escape as a gas. Evaporation is a little bit different in the sense, if you think of like a little puddle or like a lake or, some kind of stream, if it's hot, it's actually just these particles that are on the top that are escaping as a gas, while everything else down below stays as a liquid. So that's just the main difference. They're both still considered vaporization. Sublimation, this is probably a new term. This is like our dry ice. If you've ever seen dry ice, I don't know if you've ever touched it before, like in school, or if you've had some yourself. I know like a lot of times it's used in Halloween to make little like fog and smoke because it starts out as a solid and then it actually skips over that liquid phase and turns into a gas. We'll talk about at the end of these notes how if you want to see liquid carbon dioxide, there's actually a way to do that, but you have to change something other than just the temperature. Deposition is where we kind of skip. We're just going backwards from sublimation. We're starting with a gas and we actually go to a solid. One example of this is like frost on your car window. So if you park outside and it's really cold outside and overnight, you go out in the morning and there's like all this ice on your window, right? And it's hard to get off. It's definitely a solid, not a liquid. What's happened is your windshield glass gets really cold. A lot cooler than the actual air around it. It kind of loses its energy a lot easier. So what happens is all that water vapor in the air, right? It's a gas in the air. As soon as it comes in contact with that glass, the glass is so cold that the water very quickly turns from a gas to a solid. It kind of skips over that liquid phase. One thing, just make sure we should kind of already know this, make sure we're remembering that temperature is a measure of our actual kinetic energy. Okay, it's not necessarily, it's not a measure of how hot something is, even though they're kind of related, because as I add heat or add energy, the energy of those particles are increasing. But technically, temperature is the measure of kinetic energy. So as my temp increases, my kinetic energy is going to increase, okay, which means my particles are moving around faster. Like if you eat a candy bar, you're going to jump around fast. When we're looking at this actual heating curve, okay, we want to kind of talk about two different things about this graph. Okay, so this would be like if I just measured the temperature of, if I started with a block of ice, I let it melt, and then I just measure the temperature as it goes up. Maybe you've done this in like a physical science lab in 8th grade or 9th grade or something. So we kind of have two different areas we're going to look at. We're going to look at these sections where my temperature is increasing. Okay, so as my temperature is increasing, remember, we said our kinetic energy is also increasing. So what's happening are these particles, they're starting to move around a lot more. Okay, they're getting more energy. So these solid particles are starting to vibrate in place more. Those liquid particles are kind of starting to move, trying to separate, but they can't quite get there yet. Okay, so they're just moving faster. Okay, so I'll put a little key here. So if the line looks like this, that means that our kinetic energy is increasing, our particles are moving faster. Okay, if I have a flat line, oh, that's not so flat, there we go. When I'm looking at my flat areas, let me change the color here so maybe we can see it differently. All right, so if I'm looking at my flat lines here, okay, notice my temperature isn't actually increasing, right? So what's happening? Well, if my temperature is not increasing, that means my kinetic energy stays the same. Okay, so my particles aren't really moving around anymore. So I need to see, what am I actually using that energy for? Okay, it's still absorbing energy. I'm still giving it energy here, giving it heat energy. So what's actually happening to that energy? Okay, so this little picture kind of shows that. So we know that we've talked about intermolecular forces before, right? We had our hydrogen bonds, we had our dipoles, right, between our polar molecules, and we also had those London dispersion forces, okay? So what's happening is, like if I have a solid piece of ice right here, right, all of these little lines are those intermolecular forces that are holding tight all those particles together. Okay, but if I have a liquid, remember, I want those particles to be able to spread out. So in order to spread out, I have to somehow break some of these bonds between these little particles, or they're not technically bonds, I guess, these forces. I have to separate these forces. So that takes energy to do that, remember, because they're attracted to each other. So it takes energy to actually pull them apart. Think like a magnet, right? The magnet's not going to magically separate. You have to actually pull it apart. If it's a really strong magnet, it's going to take a lot of energy. If it's a weak magnet, like our London dispersion, then it wouldn't take very much energy. Okay, so now once I've used some energy, right, to break some of these bonds, now I have a liquid particle, okay, or a liquid substance. If I want to turn it into gas, I'm going to use my energy to break all of these forces, or disrupt all of these forces. And now I have all my separate gas particles. So if we look up here to these little dots here, we can kind of see in this section here, this flat line where I'm breaking my forces, we can see some of those particles are able to break away. That's because that energy is going towards separating those forces, right? Disrupting those intermolecular forces so our particles can move away. Okay, they're not actually moving any quicker. They're just able to separate now from each other where they weren't before. The last thing is what we call a triple point of CO2. Sometimes it's also called a phase diagram. Really what we're looking at in this graph is that temperature is not the only thing that can affect a phase change. We can also see that pressure can. Okay, so for example, this graph looks a little weird, okay, but I've got temperature down here on the bottom, and I've got pressure over here on my y-axis. Okay, so I can see how different phases are occurring now as I change my pressure. Okay, so in the first little block, I have a solid, a liquid, and then a gas. Okay, it always goes in this order. Doesn't matter, like the picture on your notes looks a little different, like the numbers on my y-axis might be different and my x-axis might be different. The lines may be a little bit of a different angle, but it always goes solid, liquid to a gas. Okay, so what we're saying basically is that any time my pressure or my temperature is in between these areas, it's always going to be a solid. Okay. So let's see here. Two other things you need to know about this graph is what we call a triple point. Okay. What that just means is that, I mean, exactly what it sounds like, a triple, right? All three of the phases can take place at that exact spot. We would actually do a lab in class where we actually look at the triple point of carbon dioxide. So you would take a piece of dry ice, we actually can put it in, and this is the cool video alert that's at the bottom of the weekly plan, but we actually can put a little bit of carbon dioxide in here, okay? And then we kind of seal it off up here. And then what we can actually see is as our temperature is increasing, right? So our temperature is increasing. So we're kind of moving this way on our graph. Our pressure is also increasing because it's building up all this as these solid particles kind of start turning into a gas, right? We're building up our pressure inside. So our pressure is also increasing. So we eventually get to this triple point here where we can actually see some liquid down at the bottom also, okay? And then not too long after that point, your pipette usually pops open because the pressure builds up so much, it kind of explodes the pipette, okay? This is actually something you could do at home if you could get your parents to get your hands on some dry ice. I think you have to be 18 to buy it. So if you're already 18, then you could do this. So there's the definitions of the triple point and the critical point if you need to pause to see. Oh, I didn't tell you the critical point. Critical point, that's this little dot right up here. Basically, that's the point where it doesn't really matter. Anything after this point, it's going to be a gas. That's why I call it a critical point. You'll see supercritical fluid. That means that it's a liquid, but it is almost a gas. If I increase the temperature or pressure anymore at this point, it'll automatically turn into a gas. Okay, so that's all that really means. All right, so this is just the phase diagram of CO2. It's just another example. You can see the lines are a little bit different, but we still have solid, liquid, and a gas. Okay. All right, last but not least, I want to show you how to do a couple of these problems on your on the notes. Okay, this is where we should be now. We've labeled, you should have everything labeled. So I think I have to click my pen again. Sorry. Solid, liquid, right, and then a gas. Okay, and you should be able to label the triple point and the critical point as well. Okay, so let's look at number 2. Okay, 2A. So what I'm doing is I'm just trying to say, oh, well, how can this phase change? How can we determine what phase change is taking place by looking at this graph? Okay, so instead of just going temperature, we've reached the melting point, now we have a liquid, we have to take the pressure into account too. So let's look at a temperature of 60. Okay, so that's right here. And then the pressure increases from 0.1 to 0.8. So 0.1 is probably down in here. Right, and my temperature is staying the same, so I'm just following up that same line until I get to about 0.8, which is probably somewhere right in there. Okay, so what kind of phase changes just happened? Well, I've gone from a gas to a liquid. Okay, so what kind of phase change is that? Well, I know from earlier, it's condensation. Okay, let's look at C. B is very similar to A, it's just a different example. For C, this time I'm looking at my pressure is going to stay the same. So my pressure is 0.75, which is somewhere right in there. Okay, and I'm increasing from my temperature from 0 to 75. So 0, and then 75 is probably somewhere right in here maybe. Okay. Maybe a little bit higher than that if I stay right at the 0.75. I think it's going to be somewhere right in there. It's like super close to that line. Okay, so here, if I'm going from a solid to a liquid, right, well, we just call that melting. Okay, if you think the line, the dot is over here, and you want to say it goes from a solid to a gas, that's fine. But really, it passes through that liquid stage first, I think, at this pressure. So if you want to say it melts, and then it's gonna evaporate or vaporize, that's fine. But I think it's kind of falls more in that liquid box there. Okay, and you'll have to do a couple of these for on the homework module. I think there's just one or two.